Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. A 220 volts, 50 Hz, 4-pole 3-phase star-connected induction motor is rated at 3.73 kilowatt. The equivalent circuit parameters referred to stator side are R1 equals to 0.45 ohm, X1 equals to 0.8 ohm, R2 dash equals to 0.4 ohm, X2S dash equals to 0.8 ohm and Xm equals to 30 ohm. The stator core losses amount to 50 watts and rotational losses amount to 150 watts. Using exact equivalent circuit for a slip of 4%, we have to determine the input current, power factor, air gap power, mechanical power, output power, developed torque, shaft torque, and overall efficiency. Let us first write down the given data. For rotor winding, resistance per phase referred to the stator R2 dash equals to 0.4 ohm and standstill leakage reactance per phase X2S dash equals to 0.8 ohm. For any value of slip S, expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.4 by 0.04 plus J times 0.8 ohm, that is equal to 10 plus J times 0.8 ohm. This may be written in polar form as 10.032 ohm at an angle 4.574 degree. For shunt branch, given magnetizing reactance per phase Xm equals to 30 ohm. Let us now calculate Jxm plus Z2 dash. Using values we get 10 plus J times 30.8 ohm. This may be written in polar form as 32.3827 ohm at an angle 72 degree. Now we shall determine equivalent impedance per phase. ZEQ equals to Jxm parallel with Z2 dash, that is equal to Jxm into Z2 dash divided by Jxm plus Z2 dash. Using values we get 30 at an angle 90 degree into 10.032 at an angle 4.574 degree divided by 32.3827 at an angle 72 degree. That gives us 9.294 ohm at an angle 22.574 degree. Given line-to-line terminal voltage VL equals to 220 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 220 divided by root 3, that gives us 127 volts. For stator winding, given resistance per phase R1 equals to 0.45 ohm and leakage reactance per phase X1 equals to 0.8 ohm. Expression for stator impedance per phase Z1 equals to R1 plus Jx1 equals to 0.45 plus J times 0.8 ohm. We have determined equivalent impedance per phase ZEQ equals to 9.294 ohm at an angle 22.574 degree. This may be written in Cartesian form as 8.582 plus J times 3.5677 ohm. Now we shall calculate total input impedance per phase Zin equals to Z1 plus ZEQ. Using values we get 9.032 plus J times 4.3677 ohm. This may be written in polar form as 10.0326 ohm at an angle 25.8 degree. We have obtained total input impedance per phase Zin equals to 10.0326 ohm at an angle 25.8 degree. Now we shall calculate input current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 127 at an angle 0 degree divided by 10.0326 at an angle 25.8 degree. That gives us 12.6587 ampere at an angle minus 25.8 degree. Now we shall compute rotor current per phase referred to stator side. I2 dash equals to JXM divided by JXM plus Z2 dash into I1. Given magnetizing reactance per phase XM equals to 30 ohm, and we have determined JXM plus Z2 dash equals to 32.3827 ohm at an angle 72 degree. Therefore, I2 dash equals to 30 at an angle 90 degree divided by 32.3827 at an angle 72 degree into 12.6587 at an angle minus 25.8 degree. That gives us 11.7273 ampere at an angle minus 7.8 degree. For three-phase induction motor, expression for air gap powered Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.4 ohm and slip S equals to 0.04 per unit. Therefore, Pg equals to 3 into 11.7273 square into 0.4 by 0.04, which is approximately equal to 4126 watts. Mechanical power developed Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.04 into 4126, which is approximately equal to 3961 watts. In polar form, we can write input current per phase I1 equals to I1 at an angle minus phi1 equals to 12.6587 ampere at an angle minus 25.8 degree. For star-connected induction motor, input current per phase equals to input line current. Let us now determine input power factor. Cos phi 1 equals to cos of 25.8 degree, that is equal to 0.9 lagging. Now we shall calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Given per phase stator resistance R1 equals to 0.45 ohm. Therefore, PS copper equals to 3 into 12.6587 square into 0.45, which is approximately equal to 216.33 watt. Now we shall determine total stator losses. PS equals to PSI plus PS copper. Given stator core losses, PSI equals to 50 watts. Therefore, PS equals to 50 plus 216.33, that is equal to 266.33 watt. Expression for total input power Pin equals to Pg plus Ps. We have obtained air gap power Pg equals to 4126 watts. Therefore, Pin equals to 4126 plus 266.33, that gives us 4392.33 watt. Now we shall calculate output power. PO equals to PM minus PR. Given rotational losses, PR equals to 150 watts. We have computed mechanical power developed. PM equals to 3961 watts. Therefore, PO equals to 3961 minus 150, that gives us 3811 watts. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that is equal to 1500 revolutions per minute. Expression for motor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.04 per unit. Therefore, Nr equals to 1 minus 0.04 into 1500, that is equal to 1440 revolutions per minute. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 6t. We have obtained air gap power Pg equals to 4126 watts. Therefore, Td equals to 4126 divided by 2 pi into 1500 by 6t, which is approximately equal to 26.27 Newton meter. Expression for shaft torque PSH equals to PO divided by 2 pi into Nr by 6t. We have determined output power PO equals to 3811 watts. Therefore, TSH equals to 3811 divided by 2 pi into 1440 by 6t, which is approximately equal to 25.27 Newton meter. Overall efficiency of the motor eta equals to PO divided by Pin. We have computed input power Pin equals to 4392.33 watt. Therefore, eta equals to 3811 divided by 4392.33, that is equal to 0.8676 per unit or 86.76%. Now we shall learn how to determine equivalent rotor current per phase I2' using Thevenin's theorem. For this purpose, we shall remove the load that is the equivalent rotor impedance per phase Z2 dash from this circuit. Now the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0.45 plus J times 0.8 ohm. This may be written in polar form as 0.918 ohm at an angle 60.642 degree. Rotor impedance per phase referred to the stator Z2 dash equals to 10 plus J times 0.8 ohm, that is equal to 10.032 ohm at an angle 4.574 degree, and shunt impedance per phase Z0 equals to JXM equals to J times 30 ohm. This may be written in polar form as 30 ohm at an angle 90 degree. Let us now calculate Z0 plus Z1. Using values we get 0.45 plus J times 30.8 ohm. This may be written in polar form as 30.8033 ohm at an angle 89.163 degree. Expression for Thevenin's voltage VThevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get VThevenin equals to 30 at an angle 90 degree into 127 at an angle 0 degree divided by 30.8033 at an angle 89.163 degree. That gives us 123.688 volt at an angle 0.837 degree. To obtain Thevenin's impedance, let us short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 30 at an angle 90 degree into 0.918 at an angle 60.642 degree divided by 30.8033 at an angle 89.163 degree, that is equal to 0.89406 ohm at an angle 61.479 degree. This may be written in Cartesian form as 0.4269 plus J times 0.78556 ohm. Now we shall determine Z Thevenin plus Z2 dash. Using values we get 10.4269 plus J times 1.58556 ohm. This may be written in polar form as 10.546765 ohm at an angle 8.6464 degree. We have determined Thevenin's voltage VThevenin equals to 123.688 volt at an angle 0.837 degree, and Thevenin's impedance Z Thevenin equals to 0.89406 ohm at an angle 61.479 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash back to this circuit. Let us now calculate the load current, that is the rotor current per phase referred to stator side. I2 dash equals to IL equals to VThevenin divided by Z Thevenin plus ZL, or VThevenin divided by Z Thevenin plus Z2 dash. We have determined Z Thevenin plus Z2 dash equals to 10.44 546765 ohm at an angle 8.6464 degree. Using values we get I2 dash equals to 123.688 at an angle 0.837 degree divided by 10.546765 at an angle 8.6464 degree, that is equal to 11.7276 ampere at an angle minus 7.8094 degree. Expression for induced EMF per phase E1 equals to Z2 dash into I2 dash. We have obtained rotor impedance per phase referred to the stator Z2 dash equals to 10.032 ohm at an angle 4.574 degree. Using values we get E1 equals to 10.032 at an angle 4.574 degree into 11.7276 at an angle minus 7.8094 degree. That gives us 117.6513 volt at an angle minus 3.2354 degree. We have obtained induced EMF per phase E1 equals to 117.6513 volt at an angle minus 3.2354 degree. This may be written in Cartesian form as 117.464 minus J times 6.64 volt. Stator current per phase I1 equals to ET minus E1 divided by Z1. We have determined stator impedance per phase Z1 equals to 0.918 ohm at an angle 60.642 degree. Using values we get I1 equals to 127 minus of 117.464 minus J times 6.64 divided by 0.918 at an angle 60.642 degree. That gives us 11.62 at an angle 34.85 degree divided by 0.918 at an angle 60.642 degree. That is equal to 12.65795 ampere at an angle minus 25.792 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.